understand what a single layer perceptron is. So like I said, perceptron is basically an artificial neuron. There's something known as single layer and multiple layer perceptron. We'll first focus on single layer perceptron. Now, before I explain what a perceptron really is, you should know that perceptrons are linear classifiers, right? A single layer perceptron is a linear or a binary classifier. It is used mainly in supervised learning and it helps to classify the given input data into separate classes. So this diagram basically represents a perceptron. All right, a perceptron has multiple inputs, right? It has a set of inputs labeled x1, x2 until xn. Now, each of these input is given a specific weight. Okay, so W1 represents the weight of input X1, W2 represents the weight of input X2, and so on. Now, how you assign these weights is a different thing altogether. But for now, you need to know that each input is assigned a particular weightage. Now, what the perceptron does is it computes some function on these weighted inputs and it will give you the output. So basically, these weighted inputs go through something known as summation. Okay, summation is nothing but the product of each of your input with its respective weight. Now, after the summation is done, this is passed on to a transfer function. A transfer function is nothing but an activation function. I'll be discussing more about this in a minute, right? The activation function, and from the activation function, you'll get the outputs y1, y2, and so on. So guys, you need to understand four important parts in a perceptron. So firstly, you have the input values, right? You have x1, x2, x3. You have something known as weights and bias. And then you have something known as the net sum and finally the activation function. Now all the inputs x are multiplied with their respective weights. So x1 will be multiplied with w1. Alright, this is known as the summation. Now after this, you'll add all the multiplied values and you'll call them as the weighted sum. All right, this is done using the summation function. Now you'll apply the weighted sum to a correct activation function. Now a lot of people have a confusion about activation function. Activation function is also known as the transfer function. Now in order to understand activation function, this word stems from the way neurons in a human brain work. The neuron becomes active only after a certain potential is reached. Now, that threshold is known as the activation potential. Therefore, mathematically, it can be represented by a function that reaches saturation after a threshold. Okay, we have a lot of activation functions like signum, sigmoid, tan h, and so on. Okay, you can think of activation function as a function that maps the input to the respective output. Now, I also spoke about weights and bias. Now, why do we assign weights to each of these inputs? What weights do is they show the strength of a particular input or how important a particular input is for predicting the final output. So basically, the weightage of an input denotes the importance of that input. Now, a bias basically allows us to shift the activation function in order to get a precise output. So that was all about perceptrons. Now, in order to make you understand perceptrons better, let's look at a small analogy. Suppose that you want to go to a party happening near your house. Now, your decision will depend on a set of factors. First is how is the weather. Second is probably is your wife or your girlfriend or your boyfriend going with you. And third is there any public transport available? All right, let's say these are the three factors that you're going to consider before you go to a party. So depending on these predictor variables or these features, you're going to decide whether you're going to stay at home or go and party. Now, how is the weather is going to be your first input, right? We'll represent this with a value x1. Is your wife going with you is another input x2. Any public transport is available is your another input x3. Now, x1 will have two values 1 and 0. 1 represents that the weather is good, 0 represents weather is bad. Similarly, 1 represents that your wife is going and 0 represents that your wife is not going. And in x3, again, 1 represents that there is public transport and 0 represents that there is no public transport. Now, your output will either be 1 or 0. 1 means you are going to the party and 0 means you'll be sitting at home. Now, in order to understand weightage, let's say that the most important factor for you is your weather. If the weather is good, it means that you will 100% go to the party. Now, if your weather is not good, you've decided that you'll sit at home. So the maximum weightage is for your weather variable. So if your weather is really good, you will go to the party. It is a very important factor in order to understand whether you're going to sit at home or you're going to go to the party. So basically, if x1 equal to 1, your output will be 1, meaning that if your weather is good, you'll go to the party. Now let's randomly assign weights to each of our input. W1 is the weight associated with input x1, W2 is the weight with x2, and W3 is the weight associated with x3. Let's say that your W1 is 6, your W2 is 2, and W3 is 2. Now, by using the activation function, you're going to set a threshold of 5. Now, this means that it will fire when the weather is good and won't fire if the weather is bad, irrespective of the other inputs. Now, here, because your weightage is 6, so basically, if you consider your first input, which has a weightage of 6, that means you're 100% going to go. Let's say we're considering only the second input. This means that you're not going to go because your weightage is 2 and your threshold is 5. So if your weightage is below your threshold, it means that you're not going to go. Now let's consider another scenario where our threshold is 3. This means that it will fire when either x1 is high or the other two inputs are high. Now W2 is associated with your wife is going or not. Let's say the weather is bad and you have no public transportation, meaning that your x1 and x3 is 0 and only your x2 is 1. Now, if your x2 is 1, your weightage is going to be 2. If your weightage is 2, you will not go because the threshold value is set to 3. The threshold value is set in such a way that if x2 and x3 are combined together, only then you'll go, or only if x1 is true, then you'll go. So you're assigning threshold in such a way that you will go for sure if the weather is good, right? This is how you assign threshold. This is nothing but your activation function. So guys, I hope all of you understood. The most amount of weightage is associated with the input that is very important in predicting your output. This is exactly how a perceptron works. Now let's look at the limitations of a perceptron. Now in a perceptron, there are no hidden layers, right? There's only an input layer and there is an output layer. We have no hidden layers in between. And because of this, you cannot classify non-linearly separable data points. Okay, if you have data like in this figure, how would you separate this? You cannot use a perceptron to do this. All right, so complex problems that involve a lot of parameters cannot be solved by a single layer perceptron. That's why we need something known as multiple layer perceptron. So now we'll discuss something known as multi-layer perceptron. A multi-layer perceptron has the same structure of a single layer perceptron, but with one or more hidden layers. Okay, and that's why it's considered as a deep neural network. So in a single layer perceptron, we had only an input layer, output layer, right? We didn't have any hidden layer. Now, when it comes to multi-layer perceptrons, there are hidden layers in between, and then there is the output layer. It works in a similar manner. Like I said, first you'll have the inputs x1, x2, x3, and so on. And each of these inputs will be assigned some weight, right? W1, W2, W3, and so on. Then you'll calculate the weighted summation of each of these inputs and their weights. After that, you'll send them to the transformation or the activation function, and you'll finally get the output. Now, the only thing is that you'll have multiple hidden layers in between, one or more than one hidden layers. So guys, this is how a multi-layer perceptron works. It works on the concept of feed-forward neural networks. Feed-forward means every node at each level or each layer is connected to every other node. So that's what feed-forward networks are. Now, when it comes to assigning weights, what we do is we randomly assign weights, right? Initially, we have input x1, x2, x3. We randomly assign some weight w1, w2, w3, and so on. Now, it's always necessary that whatever weights we assign to our input, those weights are actually correct, meaning that those weights are actually significant in predicting your output. So how a multi-layer perceptron works is a set of inputs are passed to the first hidden layer. Now the activations from that layer are passed to the next layer, and from that layer it's passed to the next hidden layer until you reach the output layer. Right, from the output layer, you'll form the two classes, class 1 and class 2. Basically, you'll classify your input into one of the two classes. So that's how a multi-layer perceptron works. A very important concept in multiple layer perceptron is backpropagation. Now, what is backpropagation? Backpropagation algorithm is a supervised learning method for multi-layer perceptrons. Okay, now why do we need backpropagation? So guys, when we are designing a neural network, in the beginning, we initialize weights with some random values or any variable for that fact. Now, obviously, we need to make sure that these weights actually are correct, meaning that these weights show the significance of each predictor variable. These weights have to fit our model in such a way that our output is very precise. So let's say that we randomly selected some weights in the beginning, but our model output is much more different than our actual output, meaning that our error value is very huge. So how will you reduce this error? Basically, what you need to do is we need to somehow explain to the model that we need to change the weights in such a way that the error becomes minimum. So the main thing is the weights and your error is very highly related. The weightage that you give to each input will show how much error is there in your output, because the most significant variables will have the highest weightage. And if the weightage is not correct, then your output is also not correct. Now, backpropagation is a way to update your weights in such a way that your outcome is precise and your error is reduced. So in short, backpropagation is used to train a multi-layer perceptron. It's basically used to update your weights in such a way that your output is more precise and that your error is reduced. So training a neural network is all about backpropagation. So the most common deep learning algorithm for supervised training of the multi-layer perceptron is known as backpropagation. So after calculating the weighted sum of inputs and passing them through the activation function, we propagate backwards and update the weights to reduce the error. It's as simple as that. So in the beginning, you're going to assign some weights to each of your input. Now these inputs will go through the activation function and it'll go through all the hidden layers and give us an output. Now when you get the output is not very precise or it is not the desired output. So what you do is you propagate backwards and you start updating your weights in such a way that your error is as minimum as possible. So I'm going to repeat this once more. So the idea behind backpropagation is to choose weights in such a way that your error gets minimized. To understand this, we'll look at a small example. Let's say that we have a data set which has these labels. Okay, your input is 0, 1, 2, but your desired output is 0, 1, and 4. Now, the output of your model when W equal to 3 is like this. Notice the difference between your model output and your desired output. So your model output is 3, but your desired output is 2. Okay, similarly, when your model output is 6, your desired output is supposed to be 4. Now let's calculate the error when weight is equal to 3. The error is 0 over here because your desired output is 0 and your model output is also 0. Now the error in the second case is 1. Basically, your model output minus your desired output. 3 minus 2, your error is 1. Similarly, your error for the third input is 2, which is 6 minus 4. When you take the square, this is actually a very huge difference, right? Your error becomes larger. Now what we need to do is we need to update the weight value in such a way that our error decreases. Now here we've considered the weight as 4. So when you consider the weight as 4, your model output becomes 0, 4 and 8. Your desired output is 0, 2 and 4. So your model output becomes 0, 4 and 8, which is a lot. So guys, I hope you all know how to calculate the output over here. What I'm doing is I'm multiplying the input with your weightage. The weightage is 4. So 0 into 4 will give me 0. 1 into 4 will give me 4 and 2 into 4 will give me 8. Right? That's how I'm getting my model output over here. For now, this is how I'm getting the output over here. That's how you calculate your weightage. Now here if you see that our desired output is supposed to be 0, 2 and 4, but we're getting an output of 0, 4 and 8. So our error is actually increasing as we increase our weight. Our error for W equal to 4 has become 0, 4 and 16, whereas the error for W equal to 3 was 0, 1 and 4. I mean the square error. So if you look at this, as we increase our weightage, our error is increasing. So obviously we know that there is no point in increasing the value of W further. But if we decrease the value of W, our error actually decreases. Right? If we give a weightage of 2, our error decreases. So if we can find a relationship between our weight and error, basically if you increase the weight, your error also increases. If you decrease the weight, your error also decreases. Now what we did here is we first initialized some random value to W and then we propagated forward. Then we noticed that there is some error, and to reduce that error, we propagated backwards and increased the value of W. After that, we noticed that the error has increased and we came to know that we can't increase the W value. Obviously, if your error is increasing with increasing your weight, you will not increase the weight. So again, we propagated backwards and we decreased the W value. So after that, we noticed that the error has reduced. So what we're trying is we're trying to get the value of weight in such a way that the error becomes as minimum as possible. So we need to figure out whether we need to increase or decrease the weight value. Once we know that, we keep on updating the weight value in that direction until the error becomes minimum. Now you might reach a point where if you further update the weight, the error will again increase. At that point, you need to stop. Okay, that point is where your final weight value is there. So basically, this graph denotes that point. Now, this point is nothing but the global loss minimum. If you update the weights further, your error will also increase. Now, you need to find out where your global loss minimum is, and that is where your optimum weight lies. So let me summarize the steps for you. First, you'll calculate the error. Okay, this is how far your model output is from your actual output. Then you'll check whether the error is minimized or not. After that, if the error is very huge, then you'll update the weight and you'll check the error again. Right? You'll repeat the process until the error becomes minimum. Now, once you reach the global loss minimum, you'll stop updating the weights and you will finalize your weight value. This is exactly how backpropagation works. Now, in order to tell you mathematically what we're doing is we're using a method known as gradient descent. Okay, this method is used to adjust all the weights in the network with an aim of reducing the error at the output layer. So how gradient descent optimizer works is the first step is you will calculate the error by considering the below equation. Here you're subtracting the summation of your actual output from your network output. Step 2 is based on the error you get, you will calculate the rate of change of error with respect to the change in the weight. The learning rate is something that you set in the beginning itself. Step 3 is based on this change in weight, you will calculate the new weight. Alright, your updated weight will be your weight plus the rate of change of weight. So guys, that was all about backpropagation and weight update.